Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to continue on with force reduction. As you guys probably know, this is all we're doing this week is force reduction, and I promise you by the last video, you will see why we're doing force reduction. And it's kind of ironic because force reduction is very, very, very important. It's what we do in engineering all the time. Typically a building, 3 dimensions, of course, it has loads in 3 dimensions, but what we want to do is we want to reduce those loads into 2 dimensions to make the analysis much easier, stuff like that. Now, what we're doing here is probably much more complex than you would actually see in the real world, so it's kind of ironic. So if you want to see the more realistic version of force reduction, we can skip ahead to the last video. But the real world may be easy, but the midterm is not. So although you may wonder why this is so complex and why we're making you do this, it's for the midterm. And specifically video 5.5, example 5.5, it's called a wrench. And again, I call that the kill shot in the midterm. If professors want to lower that average, they throw in a wrench. So from now, we're doing our first force reduction in 3D. But what's going to happen is over the course of this video, the next video, and then 5.5, we're going to slowly build up to that wrench. So what happens in force reduction is there's a number of scenarios that we can do. And this is the first. It's when we take our forces and we convert it into a force and a couple moment. So it's like the last example in 2D where what happens is we add all those forces and we convert it to a single force and a moment acting at the same point. And that's essentially what we're doing in this example, but in 3D. We're going to convert those two forces into a single force at point O and a moment vector at point O. And then later on in the next example, 5.4, what you guys will see is we're going to expand upon this and say, okay, well, we have a force and a moment at point O. But if I move that force, that single resultant force, that'll start to create a moment because it's going at a distance from point O. So in the next example, the force reduction is we can reduce all the forces into just a single force at a distance from the point, which would create the couple moment. And then finally, the wrench, I'm not going to tell you about. That's going to be a secret surprise because that is, it's just terrible. It's wrench. That's your worst nightmare. If you see on exam and you see a wrench, you might as well just cry because it is the worst thing that a professor could do. I'd say even compared to the final, it's the worst kind of question you can ever get. But we're going to build our way up to it. This is the building blocks, force reduction, because what we do in this example, we will need to do for the next 2 examples. So this is kind of the fundamentals, if you will. So I know you guys are too excited, so let's jump into it. Alrighty, so looking at this example, it gives us 2 forces. F1 is equal to this, and F2 is equal to that. So this is actually already really nice because typically in these examples in the midterm, you're going to have to, they're just going to give you the magnitude of those forces and they're going to make you solve for F in Cartesian vector notation all by yourself. So this is kind of like a nice little gift. And it says that they act at the end of the beam. But what the question really wants is for us to replace these forces by an equivalent force and couple moment acting at point O. So this is very important because what essentially it wants is it wants us to take those 2 forces in black and create another force at point O, something like this. So this will be a force vector, as so. And then also a moment vector. So I don't know these directions. I'm just picking random directions, but it would be a force vector and a moment vector. So this is what it wants in the end. It wants to take those 2 forces, move them to point O, and just sum up the system with 2 forces, a moment and a force vector. So there's kind of a nice little procedure for this. It's kind of similar to 2D. What I like to do for this is, one, I want to determine the moments. So moments caused by the forces. So that's where we're going to start. So moments caused by the forces. And my spelling is always horrendous. So I apologize for that because I know that none of you guys want to see that. Alrighty. So we have a force. It's in Cartesian vector notation. We can find the point. So as you guys know, we can find the moment in 3D, a moment vector, because it's going to be a position vector cross the force vector. And that's why having the force already in a vector is a gift, because we don't have to really do anything with that. So the only thing that we're really missing in these two forces is just going to be that position vector. So let's just go ahead and start solving for that. So I'll go purple, and we'll start with F1. Why not? Because we'll just go 1, 2, nice and easy. So remember, for a moment, the position vector will start at the point you want to take the moment about. So of course in this point, it's going to be point O, and then it's going to go to a point on the force. So on the force, we know this little point at the end of the beam. So we know that our position vector must look something like this. And then we're going to call this, let's just call it position vector 1. F1, R1, why not? So we know from right here that our moment, I'm just going to call it moment 1, is going to be equal to R1 cross F1. And we know that R1 is going to be equal to, it's going to be the coordinates at, let's just say 1, the coordinates of 1 minus the coordinates of where it started, which is O, or 0. You can kind of decide for yourself. But what's really nice is we know that O in this case, it's at the origin, its coordinates are 0, 0, 0. So we know that this equals 0 in the end, which is really super nice because we can cross all that crap out, and we know that the position vector 1 is just going to be equal to the coordinates of 1. So what we can do here is we can just put our nice brackets, and you're going to go, oh, they're trying to screw with me. And you are correct, because, oh, I got to erase this to kind of help you guys see. So they do this a lot in midterms and final exams. So this is, you guys haven't seen it yet in my videos, but this is a golden case of what they do. If we look at the long dimension of the beam, we see it's 4 meters. However, if we look at this dimension of the beam, it's in millimeters. Love to do that. A lot of people would put 4 millimeters or the opposite and go 250 meters when just by the scale. Of course, that makes no sense at all, but they love to do that. So please, please, please pay attention to your units because it'll be very important. In these kind of cases, I prefer to convert everything to meters just because 4,000 millimeters, well, it just seems a lot. I don't want my numbers huge. So I'm going to go the easy route, go meters. And if we're looking at F1 here, first thing we're going to want to do is X. And well, we know that that's going to be 4 meters in the X direction. So we're just going to go 4I. Looking at the Y direction, we can see that it is 150 millimeters, but it's in the negative direction. So we're going to go minus 0.15J. So 0.15 meters is the same as 150 millimeters. And then our last one is going to be in the Z direction, which we see as 250 millimeters. So we're going to go plus 0.25. So 0.25 meters is 250 millimeters. And that's going to be in the K direction. And we can end that bracket, and we're going to state our units, which is meters. Now this is important. For example, you could have went millimeters. That is completely fine. You would have 4,000 and then 150 and then 250. But in the end, you're going to have to put that millimeters. So as long as you're aware of that, everything will be completely fine. And that's our position vector. And we already know that our force vector is given to us in the question. So I'm just going to write it down here for fun. So we know the F1 is negative 4I, and then plus 2J, and then minus 3K. So plus 2 in the J direction, and then minus 3 in the K direction. So I'm going to end that. I'm going to just double check we're correct. And then, of course, units are kilonewtons. So we're just going to put kilonewtons. So we know that moment 1 must be equal to R1 cross F1. So what we can do is we can start writing our determinant or our matrix, whatever you guys prefer. And we know that the top row for this is always going to be I, J, and K. Always. So that's kind of a given. If you forget about that top row, I actually believe it's on the formula sheet. So just take a quick skim at the formula sheet if you guys are curious about that. Now, the second row for this is always, always, always going to be the position vector. You guys know this already. You guys know how to take moments, so this should just be review. So it's just going to be the position vector. So it's going to be 4 and then negative 0.15 and then 0.25 for the last one. And then our last one is going to be the force vector. So we're going to have negative 4. We're going to throw in a 2. And finally, a negative 3. And we're just going to dot that all up. So I usually tell people, make sure you write it in this form. I know a lot of you guys can just go right into the math. You guys are very smart. But as a marker, for example, this is one of the things we look for. So if you don't get the final answer right, one of the things we're going to check is, do you have this matrix set up properly? Because just judging by your matrix, we can easily tell where you went wrong. If you, for example, got the final answer wrong, but your matrix was correct, we know it's probably just a little calculator mistake, something like that, so you probably won't get docked very many marks. However, from here, we can easily see if your unit vector, not your unit vector, your force vector and your position vector are correct. So that's why it's always very important to check that out. So again, I'm just going to solve for the moment directly like the last video. I'm not going to show you guys the fish method. You guys are very well aware of the fish method. If you guys want more practice with the fish method, please, by all means, go back into the last week and just check it out. Because this is very, very, very important. You guys will want to know how to solve these later on. So looking at the I component, I'm just filling out all the entries based on the method. So we know that's what's going to be in the I direction. And then we also know that there's going to be a J component. So in brackets, it's going to be 4 times -3. And then minus 0.25 multiplied by -4. And that right there is in the J direction. And finally, we're going to have a K component, so plus, and then we're going to do the brackets. And then for the K, it's going to be 4 and 2 minus -0.15 by -4. So that is our moment vector for force 1. So that's just force 1. We're going to have to do this again after. That's going to have kilonewtons times meters. So if you guys did opt to, of course, pick the millimeters instead of the meters, that's where this would change a bit. Of course, you're going to get a different answer. It's going to be different. But in your units, you're going to have millimeters. So it's going to correspond to that. So we're just going to simplify it real quick by just doing all the calculations and get a single vector. So we know that M1 is going to be equal to -0.05I. And then we're going to have plus 11J. Perfect. And then we're going to finish it off with a plus 7.4, and that's in the K direction. So in the bracket, we know this is kilonewtons times meters. So if we look at this, we haven't done anything new really. This is just simply finding the moment about a point caused by a force. And this was last week. This is nothing new, but it's just one of the steps that we're going to need to follow for what we're going to do a little bit after. So I'm just going to erase this real quick. We've accomplished the moment due to F1, so we're good to go. So now we're going to go the moment due to F2. So we're just going to move on through all the forces, and that's kind of the procedure. We just want to go all the way around. If there was 3 forces, we'd do this again for a 3rd force, and so on and so on. So we're taking the moment about O. We're going to go all the way to the point F2, so it's going to be a line like this. And we know this is going to be our position vector right here. So we're just going to call this position vector 2. Nice and easy. So we know if we go down here, we know that our M2, so our moment caused by force 2, is going to be equal to position vector 2 cross the force vector 2. And again, we already have the force vector 2. So only thing we really need, that position vector 2. So we know this is going to be equal to the point at 2 minus basically the origin. And this is nice. We know that the origin is 0, just like the last one. So let's get rid of all that crap. So it's equal to just the coordinates. So then I can just go in brackets like this right here. And we see that it's actually the same as R1. The only difference is in the Y direction, instead of minus 150 mils, it's plus 150 mils. So we're just going to go down here. We're going to go 4I plus 0.15J, I just about said K, plus 0.25 in the K. And the bracket, and of course this will have units of meters. So, just like before, we can solve for our matrix for the moment. So I'm just going to put equals, go down a couple lines. First row is always the I, the J, and the K. Second row, always going to be that position vector, so it's going to be 4, 0.15, and 0.25. And finally, we're going to finish it off with that force vector. So if we look at the top, it's going to be 3, -4, and -2. So we're going to just throw in the 3, -4, and -2. So, ta-da! And we just go through all the math. So we know that it's going to have 3 components. We're going to start off with a squiggle bracket, and we're going to focus on the first one. It's going to be 0.15 times -2 minus 0.25 times -4. Oops, -4. What am I doing? And it's funny because that one negative will mess everything up. So it's really, really bad. So that's in the I. And we're going to go minus. We're going to start throwing crap at the j direction. So it's going to be 4, -2. -2, and then minus 0.25 times 3 in that bracket. So that's going to be the j direction. So again, if you guys are kind of unsure where I'm getting these numbers from, well, I know you guys all know I'm getting them from that box there, but if you're wondering the procedure on how I'm arranging these numbers, this was covered last week. So please feel free to go check out those videos. This goes in depth on how I'm getting this. But again, if you guys really want, your formula sheet does have a indirect guide on how to do it. So we're going to go to the final column. So it's going to be 4, -4 minus 0.15 times 3. And the bracket, and this will be in the k direction. So we're going to end this, and this will be kilonewtons times meters. So we know that M2 is going to be equal to, and in brackets, and what I get is 0.7i after doing all the math, 0.7i plus 8.75j in the j direction, and then minus 16.45 in the k direction. And the brackets, and this of course is going to be units of kilonewtons. I was going to say kilonewtons times meters. So first step is done. I want to take all those external forces that are on the beam, basically convert them, or not convert them, that's the next step. I want to find the moment caused by all of them about the point that I'm interested in. Of course, this point says in the question, point O. So I found both of the moments caused by point O. So my second step that I want to do in this is I want to do my resultant force. So actually, let's just get rid of this. I want the resultant force. So resultant force. And we know that resultant force is just going to be the summation of all those forces. So in this case, we have 2 forces, so it's going to be F1 plus F2. You guys, okay, well, actually, that's really, really easy because we can do this really quickly. So in brackets, for the x component, we're going to have 2. So what we're going to do is take the 2i components, which are -4 and 3. So we're going to go -4 plus 3. That's in the I component. Plus, we'll take a look at the j component. So we got 2 and -4. So it's going to be 2 minus 4. 2 minus 4. And that's in the j. And we finish it off with whatever's in the k. Look at the top. We got a -2 and a -3. So we're just going to go -2 minus 3. And that right there is in the k. Finish off the brackets. And this is, of course, force. So the units will be just kilonewtons. So real quick, we're just going to make this just a little bit nicer. So we're going to have -1i minus 2j minus 5k. So that right there is our force vector. So just going to finish it off and throw in the kilonewtons. So if we're looking at point O right now, this is the force we're going to put on it. When the question asks us for the equivalent force, that's our resultant force right there. So we can just put a little check mark next to that because we just figured that out. So that was actually not too bad. As you guys will see, the hardest part really of these force reductions is just finding all the moments that the forces cause. That's just kind of the real pain in the ass. The rest is actually just a nice simple addition until you get to wrenches, and the wrenches just suck in their own way. But you guys will see that later, so I won't spoil the fun. So found our resultant force. Next thing that we're going to want to do is just our resultant moment. So resultant moment. And surprisingly or unsurprisingly, the resultant moment is going to be the exact same procedure as the resultant force. So it's going to be all of our moments added together. So we've got M1 and we have M2. And that's it. We just add those two components together. So it's the exact same as before. So what we're going to get is we're going to get a vector and it's going to have an I component. So we're going to go up to what we solved and we see that M1 has negative 0.05 in the I and M2 is 0.7. So we're going to have negative 0.05 plus 7. And that's in the I. Oh, sorry, it's 0.7. So let's just get rid of that real quick. It is 0.7. So plus 0.7. And that's in the I direction. Plus, then, okay, let's go take a peek at the J components. So we got 11J for M1. And we see that we got 8.75J for M2. So we're just going to go down here. And we're going to go 11 plus 8.7J. Is it 7 or 7.5? 7.5J. So 11 plus 8.75. And that's in the J direction. And of course, we also have a K component that we cannot forget. So we go up here, all the way to the top. We see that we got 7.4 for M1. So let's go 7.4. And remember the last K was negative, and it is negative 16.45. So minus 16.45. And that right there is the K component right there. And this will have units of kilonewtons times meters. And that just looks absolutely awful. So let's give that another try because this is not what I was going for. Okay, a little bit better. My writing's still garbage, but that's fine. All right, so we can just do the math real quick to make this just a bit nicer. So we know that after adding them, it's going to be 0.65 in the I direction plus 19.75 in the J direction. And then we ended off with minus 9.05, and that is in the K direction. Ta-da! Units, it's a moment, so kilonewtons times the distance, which is meters. So kilonewton meters. So the best thing that you guys can do to finish off these questions is you're just going to want to draw point O, basically. So if I were to just make a little origin right here, oops, that's not what I wanted to do. Just make a little origin like this. Actually, I'm just making this so bad. Let's go down real quick. Make this a lot nicer. So let's make our point O. It's going to be something like this. It's going to have, of course, it's 3 dimensions. So we know that this is Z. We know that this one is Y and this one is X. And all I want to do in here is just draw my 2 equivalent force systems. So we look up here to the resultant force. It's negative in all directions, so we can just say that the force vector, let's say, goes something like this. And we know that this is, in brackets, FR, which is equal to, and then we got the negative 1I minus 2J minus 5K. So again, not really to scale whatsoever, but it's fine because I'm just drawing kind of the final diagram of my equivalent force system at point O. So I go up here, I also have a moment. It seems to be going pretty positive besides K, so let's just draw it like this. Good enough. So remember, a moment vector, it's the same as a regular vector, except it'll have a little kind of rotation about it. And we know that MR, oops, will I have enough room? I'm just going to shift this up a bit or else it's going to look like garbage. MR is equal to, in bracket, 0.65I and plus 19.75 in the J. Oops, not I again. Oh, my pencil's kind of making a clicking sound. Let's just get rid of that. And the J, and then minus 9.05 in the K. And the bracket, and this is kilonewton meters. So this is basically what we wanted. Oh, and we should probably just also put that this is point O. Point O. So this is what the question wanted. We took those two forces, F1 and F2, and then we made them into a single force at point O. So again, moving forward, I'm just going to box this because this is technically my final answer. This box is going to be really difficult to try and do something like this. So this would be a good final answer. This is the first step for the future. So right now we're at a point where we convert all our forces into a single force and a single moment at a point. Now, this is perfect for this question, but what we're going to learn to next is, okay, well, we know that if we move a force vector around, not along its line of action, of course, if we move it off its line of action, it's going to start to create a moment. So now the question is going to be, where can we move this FR so that it creates that moment that we have there too? So basically, we have a force and a moment. How can we simplify the system so that it's just a force? Just a force. And that is a perfect question for a midterm. They'll say, where will that force be on the XY plane to create that moment? So that's what we're going to get into next. But as I was saying, to do that, we always need this step. To do the wrench, which is what I've been alluding to is just terrible, 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 we still need this step. This step is very, 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 very important to get to here. So make sure you know this, and we'll continue on in the next video, and we're going to kind of apply it further and further until we get to the main thing, which is the wrench. And then the last example, of course, is the realistic example. And as you guys will see, it's not as bad as any of this. But even though reality can be nice, your midterm's not. Your midterm's kind of a bitch. So we'll get to that later on. So thank you so much for listening. I'll see you guys in the next video.